important because when I say there is conservation of linear momentum, I have to study everything together. So I'm just repeating the last class, okay? But we'll do it a bit fast. Probably I'll take 5 minutes for this. So first revision, a very fast revision of the last class. And in the last class, what we started was our aim is to discuss the conservation of linear momentum if the coordinate corresponding to the displacement is cyclic. Okay, so the coordinate doesn't appear in the Lagrangian, that displacement was important. Okay, so we did say, I think let's just skip this slide because I've already discussed this yesterday. We said that the translation will actually remain invariant under certain translation. Okay, so under certain operations. So what happens is, if you're basically having a coordinate which is cyclic, which you can ignore, okay, that kind of coordinate, if involved, will actually not affect the translation. Okay? That is what we do. And then we consider Qj to be the generalized coordinate. Okay, so Qj is your generalized coordinate. Okay, and these notations are important, we should remember. And dQj will represent the translation of the system as a whole in some direction. And this small Qj will not appear in the kinetic energy. So this also we saw, because kinetic energy is half mv square, and then Qj is nothing but representation of the position, so it doesn't appear in kinetic energy, so we usually say that's ignorable. Okay, so since this depends on the velocity, which involves time derivative, so we usually say that this is important, right? Del t del Qj dot is equal to 0. Okay, so that's important. Okay, so then if we just go back to this conservation, okay, and if we basically consider a conservative system, what we see is this, that delta V delta Qj dot is equal to 0 and delta V delta Qj exists. Okay, so why delta V delta Qj dot is equal to 0 is something which comes from here. Okay, so if you look into this Qj dot, okay, let's focus here. Okay, I think we can focus it here. So Qj dot and L is equal to T minus V, and then del L del Qj dot can be written as del Qj dot of T minus V, right? But then last class we also saw that delta V delta is not dependent on Qj dot, it's just dependent on T. So the term delta V delta Qj dot will become 0, we'll just be left out with Qj delta T delta Qj dot, and that's the reason we have it here. Okay, so delta V delta Qj dot will be 0 and delta V delta Qj will exist. Okay, it's there. So then we can actually go back to the Lagrangian, and then we know the equation is d dt of del L del Qj dot minus del L del Qj is equal to 0. So d dt of y del L del Qj dot can be replaced by del T del Qj dot is something which is here. Okay, so this is the del T del Qj dot. I think I can use the pen here. Okay, so this is the del L del Qj dot can be written as delta T delta Qj dot. Okay, and then we can just replace it here, and delta L delta Qj dot is nothing but minus of delta V delta Qj dot, so we'll replace it here. So the point here is that you have to write it down in your notebook so that you can actually read it together and understand it better. Okay, it's very simple. And then we also saw that delta T delta Qj dot is nothing but the generalized momentum. Okay, so dT of Pj dot Pj, okay, which is nothing but the generalized momentum, is equal to minus of del V del Qj dot. Simple maths. This relation we are going to use, that's why I have marked it as number 1. And then this P, which is nothing but generalized force in terms of potential energy is minus del V by delta Qj. So these are important relations. Okay, so this is your rate of change of momentum, and this is the force, more specifically generalized force. Okay, so this is the relation that we have derived yesterday. I think this is important. And then we actually talked a bit about the generalized force. So when we talk about generalized force Qj, it is basically the component of the total force, but then there is a catch. Okay, this is important. Why? Because we said that when we talk about a force and we are talking about the conservation, we are talking about the conservation of linear momentum and not angular momentum. So if you're talking about the linear momentum, the force that is being applied should be along the direction of translation of Qj and Pj, not along any other angles. Okay, because if it makes an angle, it basically will set off a rotation. So it's not a force, it's a torque then. Okay, not talking about torque here. So if Qj, so what is our aim now? The Qj should be along the same direction as Qj and Pj. Okay, and if you do that, this equation 1 will represent the equation of motion for total linear momentum. So this equation we have will represent the equation of total linear momentum. Okay, so the aim is actually to find out this, to show that this is in the same direction as Qj and Pj. So this is what is being done now. Okay, so what we say that the generalized force, okay, the generalized force Qj is summation I Fi delta Ri delta Qj. Okay, so what is Ri? Ri is nothing but your position vector, and dqj is nothing but the component in that particular direction. So we already talked about vectors, and if you want to define the direction of vectors, you usually take that relation. Okay, so this delta Ri by delta Qj, you can straight away write it down as n cap, but then I'll just take a step ahead and say that this delta Ri with respect to the x-axis can be written as n cap Qj. Okay, n cap Qj, delta Qj, right? So in that case, we can simply write it down as delta Ri delta Qj is equal to n cap, right? So I think I corrected it yesterday. It's the same slide, so that is the same error. So n cap. So this is n cap. So delta Ri delta Qj is n cap. So we'll just replace it with n cap. N cap. Okay. So if you do that, we actually get this relation. So this is the relation that we have here, okay, which is important. So this is your generalized force, okay, and what does n cap represent? N cap represents the direction, and this n cap says that the direction is along Qj or Pj. Okay, so this actually is important here, which represents the component of the total force along the direction of n. Okay, well, let's not repeat this same thing, and then we can actually find out what is the kinetic energy. Okay, and then T is equal to half mi dot square. Okay, and then we can actually find out the momentum. So we know that generalized momentum is nothing but the uh, uh, del T by del Qj dot, right? I think this is we have seen last class also, del T by del Qj dot. Let's replace this uh, T by half summation mi Ri dot square, and if you take del del Qj of Ri dot square, you get 2 Ri dot del Ri del Qj dot. Please do it, and then you see that this is nothing but mi Ri dot delta Ri dot delta Qj dot. So this is where we stopped. Okay, this is where we stopped yesterday, and then we will continue from here. Okay, so what is important here is this particular term, I guess. Okay, so this particular term is important here. Okay, so we will take this term and then look here. So see, this is your momentum. So if the force is along this direction, the momentum should also be along this direction. So if you do this representation, does it represent along the same direction? The answer is yes, because delta Ri dot, every expression without a dot or with a dot carries a meaning here. So in exam also, try to understand and write, don't miss this out. Okay, so delta Ri dot means delta Ri delta T, delta Qj dot means delta Qj delta T. Okay, so that means it will become delta Ri delta Qj. So we will continue. Okay, we'll continue with this. So here what we can say is this, that when we do this, okay, okay, so what we do is this, MIVI delta Ri delta Q, delta Ri dot by delta Qj dot, delta T gets cancelled, delta Ri by delta Qj, and we have already seen that delta Ri by delta Qj is equal to n cap. So this is the direction. So I can just take this n cap out and write down summation of MIVI. So mass into velocity means it is nothing but the momentum, right? So if we take that, we get Pj. So Pj, which is this, okay, so this is your Pj, right? So this is your Pj, is this. So Pj is the component of total linear momentum, because this is linear. Component of the total linear momentum along the direction of translation, because there is a n cap there. So you see everything here, whether you take n cap, whether you consider mi, vi separately, all has got a meaning. Okay, and hence we can say that Pj dot is equal to Qj. How? Again, go back. Okay, see here, we actually found out this relation. Pj dot is Qj, and then I have gone here and said that Pj dot is equal to Qj. So in between what I have done, okay, in between what I have done, this is what I have done, and this is what you should remember for your exam also. Don't directly jump to the answer. You have to understand here from the classical point of view that I have written Pj dot, I have written Qj, but I did not say along which direction, because this may be a force, and if it is at any angle, it doesn't remain as a force, it becomes a torque. So I have to first prove that this Qj and Pj are along the direction of Qj and Pj. Okay, so how do I do it? I basically just consider some coordinate system, okay, and then write down this the generalized force in this particular form. Okay, and then using the basic idea of vectors, I say that this is n cap, and then I show that this is the generalized force, which is nothing but n cap. So this Qj represents along the direction of n, okay, or along the direction of Qj. If it is represented along the direction of Qj, it automatically represents the direction along Pj also. Okay, but then we can do that, okay, manually. So we'll do it for Pj. We'll do it Pj is equal to summation mi ri dot delta ri del Qj dot. Just do the replacements in the appropriate places, and then we take n cap. So we get this. So this is the relation that we have now, and then actually we can surely say that Pj dot is equal to Qj. Okay. So we have this now, okay, and then what will be our concluding statement? The concluding statement will be this, that this Pj dot is equal to Qj is the equation of motion for total linear momentum of the system. Okay, this is the equation of motion for total linear momentum of the system. So you know that whenever we write down an equation, okay, whenever we write down an equation, let's say I will take this, okay, let's say f is equal to ma, right? All of us are very comfortable with this. Whenever we write down an equation, and let's say I write down f is equal to ma, that is the equation, right? That is the equation of motion. Here also it's the same thing. Pj dot is the force, this is the force, so this is basically representing force. So that means this is the equation of motion in terms of generalized force of the system. Okay, so we'll take that equation, and then based on this we can actually say that if this Qj is cyclic, then capital Qj is equal to minus del V del Qj is 0. Okay, again I think I should go back to the previous slide. Okay, where did we get this? Here we got it here. Qj is minus del V del Qj, right? So if we say that, and if we say that this particular Qj is cyclic, okay, it does not appear in the Lagrangian, okay, L is equal to T minus V. So if it does not appear in the Lagrangian, it does not appear in the potential energy also. This is any coordinate, okay, it is any coordinate. It's not that the potential is independent of position. No, that's not true. But the thing is Qj does not appear. So that particular coordinate does not appear. Okay. So if that particular coordinate does not appear, we do say that Qj is equal to minus del V del Qj is equal to 0. So that means Pj dot is equal to 0 because Pj is Qj. So this is means this is also Pj, right? Pj dot. So if this is Pj dot, this is 0. So that means delta Pj delta T is equal to 0, or Pj is equal to constant. So if Pj dot is equal to 0, obviously it's a constant, right? It's something like this. Just written it so that we are clear on all steps. dx dt if x is constant. So what's our conclusion? Our concluding remark is, read this very carefully, if the given component of the total applied force vanishes, so that means capital Q vanishes, the corresponding component of the linear momentum is conserved. So in general, we can say that if Qj is cyclic, it's a cyclic coordinate, it does not appear, then the total applied force will vanish. And then if the total applied force vanish, since it is related with Pj dot, comes from the basic of Newton's second law, we can say that the momentum is conserved. Okay. So what do I exactly learn from this? The important part here is that if we actually have a cyclic coordinate, that means I have, if I want to define a system, we have got so many coordinates to tackle, okay? So many coordinates to talk about. But then if we are having so many coordinates, the problem becomes more and more complicated. So suppose I write it in terms of generalized coordinate, and some of the coordinate I don't need to consider now. So that means they become cyclic or they become ignorable. Then the equation becomes simpler. So if you consider that cyclic coordinate, the linear momentum in terms of that particular coordinate will be conserved. Okay, and this is what we proved here. So you see, there is a lot of things to know here, and I think it's a bit long because this is what is important here. This is what is real classical mechanics is all about. We start from here, okay, and then we do give a basic idea, basic base of this to take the Lagrangian, do the solution, find out it in terms of generalized momentum, okay, and then we say that we have to show it that it is along Qj or Pj. We do that, okay. Once we finish that, we actually consider it to be a relation Pj dot is equal to Qj. Once that is done, we do say that if we consider the Qj to be cyclic, till now we did not say Qj is cyclic. So we say that Qj is cyclic, and then we say that this is nothing but equal to 0, and then we say Pj is constant. So this will be a question, important question for your exam, okay, and this will be, I think, it deserves 5 marks.